For our little discussion, our first discussion on conformal field theory. The main thing I wanted to discuss now, before turning to going back to string theory, is this weak theorem that we talked about. We used it a lot, but we used it for conformal nominal ordering, which sometimes I don't want to rely on something that you half remember and something that's not exactly what we were doing, so I just wanted to give you a better understanding of this theorem. Okay, so firstly, let's start with the following. Suppose I've got an integral which is dxi, the product of finite number of variables, dxi exponential of minus alpha ij xi xj by 2. Okay, this is the integral I want to study, and so let's use the word gij for alpha inverse. Alpha is symmetric, real, everything good. Okay, and let's use the notation gij for alpha inverse. Okay, when all of you know that xi xj, the 2-point function, is equal to gij. Is equal to gij. You could prove this by taking a source and completing the square and so on, the usual things. So maybe we should put the ij up. Okay. Now, what is the statement of Weak's theorem sort of precisely stated? First, suppose we were interested in doing the following. So we had product over I dxi, exponential of minus alpha ij xi xj by 2, and we've got some f of xi's. I don't care what it is, some function of x's. I want to do this integral. Okay? So, what is the claim? Let's see, the claim of Weak's theorem can be stated in an elegant way. Okay? It is the product over I dxi, that this thing is simply equal to, okay, let's do that divided by integral product over I dxi exponential with no f's, which is some determinant, some normalization determinant. So this is, now watch this, exponential of gij del by del xi del by del xj acting on f of xi. And in the end, after you've said all the differentials, we're supposed to set x equals 0. Okay, let's first see that this is what you already know. Let's suppose that we had, suppose f was quadratic, xi was equal to xi xj. Okay, then we'd bring down one factor of this. You see, we'd Taylor expand the exponential. We'd Taylor expand the exponential, and we Taylor expand the exponential. Only the first term could contribute, because there are 2 x's, so 4 x's, 4 derivatives given. Notice that g, by the way, is a constant, right? So nothing to do with x's. Okay, so we bring down the derivatives of the exponential, only the first factor contributes, and clearly what we will get is gij. That's obvious. Okay, now suppose we had xi, xj, xm, xn. To start with, suppose xi, xj, xm, and xn were all distinct. Works out also when they're the same. Okay, what will we get? We'll get one factor of this for every possible pair. Okay? And that is Wick's theorem. You contract in every possible way. Okay? I'll leave it for you to check that when some of these x's are the same, the factors also work out right. Okay, there's no issue. Okay? This, of course, is not something you just assert. It's something that's quite easy to prove. How would you prove this? Well, one way of proving this is to write down a generating function for correlation functions. You start with this and add plus ji xi. Then if you want to bring down this f of xi, you just have to differentiate every insertion of an xi is an insertion of a derivative with respect to a ji. Okay? And using that representation, you will quite easily be able to prove this statement. I'll leave that to you. It's a simple manipulation with Gaussian integrals. Okay? So this is an elegant way of computing any expectation value, a formally elegant way of computing any expectation value, now, I've been a bit inaccurate here because really, you see, well, if this is like sum over all I and all j, I should divide by 2. As you see, when we acted on xi, xj, there would be two terms that contribute. Let's suppose we acted on x1, x2, there would be g1, 2 and g2, 1, and they're the same. So that overcounting is correctly taken into account if you divide by 2. So I'll put that 2 by 2 and we'll on sums, and now we're good. Okay? So we want to compute any expectation value of any number of x's within a Gaussian integral. Okay? Within a Gaussian integral, this is what we do. We use this. Okay. Now, I'm going to do the following. I'm going to do this. Next thing I'm going to do is to define the analog, the thing that when we use this for field theory will become normal ordering in terms of such an operation. Okay? And my definition will be as follows. Consider an expression f of xi. If I want to define normal ordered f of xi, okay? Okay. Let's remember, just to motivate, let's remember what we do. Suppose we had an expression with unnormal ordered, we contract, and whatever's left behind is normal ordered. Okay? And so we get the following claim that f of xi, okay, following this in terms of these things is just a definition, but it will be reproduce the same definition as normal ordering for our field theory, is equal to exponential of minus gij by 2 del by del xi del by del xj on f of xi, normal order. The only difference between what I've written here and what I've written here is I haven't set x equal to 0. Okay? So this part picks out the expression that is one normal order in the f of x's. We always think of f of x's being polynomials or things that can be expanded in polynomials. I mean, Taylor expanded. Okay? Because here we get some expression, which is still some polynomials in whatever those polynomials are, but formally are called normal ordered things. Okay? When we set x equals 0, only the 1 contributes. Is this clear? Now, why is this the same thing as what we do in field theory? It's the same thing because you see what we do is we take an expression and contract away things, and whatever's left behind is normal ordered. That's how we express an unnormal ordered quantity in terms of normal order. By pairwise contracting everything, all options, and whatever's left behind is normal order. And that's exactly what we've done here. That's clear? Okay? So this, when I apply it to field theory, okay, this thing here will be the standard definition of normal ordered insertion of an operator. Okay, so I keep saying when I apply it to field theory, what will the role of xi be? Xi, of course, will be x of sigma. And this expression here will be replaced by g of sigma minus sigma prime by 2 del by del x of sigma del by del x of sigma prime. Is this clear? Right, so this will be e to the power. Why have I put that? I'm sorry, why did I put the minus here? Neither here. I'm sorry. Yeah, so once we have the minus, once we have the 2-point function, it's whatever it is. Is this clear? Okay. Now, one advantage of this expression is that it's easy to invert. You see, what we have here, once we've evaluated this, is some polynomial in x's. What is this mathematically? It's a rule given one function for producing another function. Is this clear? So suppose I started with a quadratic function. It will be quadratic plus constant. It will be xi xj plus constant. The whole thing will be normal ordered. It's a map from functions to functions. A well-defined map. Okay, now we can ask, does this map have an inverse? But it's obvious that it does. Because let's act on this. This is some function of x's. This is some other function of x's in the end. Now let's act on this with the same exponential but with a minus. And since derivatives commute with each other, we can combine them so that on the right hand side it becomes 1. Okay? And therefore we conclude that exponential of minus gij by 2 del by del xi del by del xj on f of x is equal to normal ordered f of x. I call this g, maybe. That if I give you a normal ordered expression, there's some map, right? I'm defining some map.
So, more technically, the left-hand side that you have defined here is the expectation value, right?
No. It's not an expectation value. It would have been had we said x equals 0. But you see, when we do Wick's theorem, we expand an operator in terms of normal ordered operators. We don't only keep the expectation value piece. Is this clear? This is a very important point. I'm defining a map between functions and functions for you. The constant part of that function is the expectation value. But there's much more information in the function than just in the constant part. Is this clear? Okay. Obviously my map is linear and so on, right? I take f plus g, I act with the exponential on f plus exponential on g. It's a good, nice standard map.
So
yes?
In the Wick's case, I understand why it was exponential. You only get quadratic. You only get even terms, right?
You contract away pairwise.
No, I remember you still only do this, you're also getting odd terms.
Oh, you will get odd terms from here. See, suppose Exactly. So suppose you have xi, xj, xk. When we expand this out, we will get gij times xk plus other things. So this is really the same as Upmanyu's question. We're not just taking expectation value. We're expanding out in terms of normal order. Okay? So what we've done, from this point of view, normal ordering is a map from one function to another. Okay? And it's a map which we can easily invert, as I've just done. Obviously. All good?
Representation of the same function in another way. Can we put it like that? Because
there's as much information in one function as the other.
Yeah.
It's a linear map from one function to another. Okay? It's okay. Now, what now what am I interested in? I am interested in the following question. Okay? I'm interested in the following question. I am interested in, suppose I have a normal ordered function. Okay? And I multiply it by another normal ordered function. I want to obtain the result of that in terms of a third normal ordered function. Okay? So the question I'm going to ask is the following. Suppose I take normal ordered f of x and multiply it by normal ordered g of x. Can I write my answer in terms of normal ordered some things? Okay? Well, so let's see. But as a function, yeah. So what is this thing? This thing, by normal ordered f of x, I mean this operation. So let's write it down. Yeah, right. So this, by definition, I'm just going to write it out. As a function, this thing is exponential of plus gij, gij by 2, del by del, delta by delta xi, delta by delta xj.
This is minus. From this definition.
Thank you, minus f of xi. And then as Indranil said, what we're going to do is now use a separate variable for the second function. Let's call those y's. In the end, we'll set all variables equal. Okay? Well, so this g was times exponential, this product is this times exponential minus gij by 2 del by del yi del by del yj times g of yi. I could have said x, but it's going to be useful for what I do next. In the end, setting x equals y. This is what these product of normal ordered functions means. Okay? Now, what do I want to do? I want to write this as exponential of, I want to write this as exponential of minus gij by 2 del by del xi del by del yj del by del xj plus del by del yi del by del yj of some function of x's and y's.
Wouldn't it be useful to write different indices for the second row?
No, but they run over the same indices.
No, I mean.
I just made them y's. It's the same. They were only. So, what I want to do is to write this. So I'm just doing the following manipulation. Okay. This thing is equal to exponential of minus gij del by del xi plus del by del yi del by del by t xj plus del by del yj. Okay? Acting on, but now you see, this is what I wanted, but it's not exactly what I have here.
Yeah.
Because this thing also has cross terms.
Yes.
So let's just add in the cross terms plus gij, and now the 2 will go away. Del by del xi, del by del yj on f of x, g of y. Is this clear? But this, by definition, whatever it acts on, normal orders it. Okay? And therefore, what we've concluded is that normal ordered of f times normal ordered of g is equal to exponential of gij del by del xi del by del yj of f of x g of y in the end setting x equals y. The first term was needed for the definition of normal order. You see, when we we're in the end interested in setting x equals y. So this derivative should act on both x and y. So this term is needed for what? Okay? So that's why the first term is just producing this normal ordered set. Whatever's left behind is what is normal ordered. Will be star product, correct. Correct. It's very similar to that whole logic. Yes.
Just a symmetric thing.
That's right. Okay? So do you understand this? So this way of thinking is a beautiful formal procedure for taking normal ordered, suppose I've got a normal ordered expression multiplied by another normal ordered expression for expressing the result in terms of normal order. Now, if you think about it, it's totally obvious. Okay? Because what this is saying is cross contract. You can't contract within two x's because it was already normal order. You can't contract between two y's because they were already normal order, but you must produce every contraction that you can, and what's left behind is normal order. It's what we were doing intuitively yesterday. Okay? But this is the formal justification for that procedure. And you know, as the Americans like to say, this is not rocket science, okay? it's trivial. It's trivial manipulations with Gaussian integrals. We've done nothing, nothing fancy at all. But it follows so beautifully. Okay? So all the OPEs we calculated yesterday, what were we doing? We were taking a normal ordered expression, multiplying by another normal ordered expression, re-expanding in terms of normal ordered expression. What we were doing was contracting every way we could, cross-contracting between terms, whatever was left behind, saying that was left normal ordered. And that is now sort of clear. Okay? So now applying this definition, so what now let us be more clear. So when I write normal ordered expression of fields, what do I mean? I mean exactly this. Okay? With the role of this gij by 2, del by del xi, del by del xj being played by this quantity. What?
From the first, I mean, normal order of fx, normal order of gx,
Mhm.
y. Then the results are without that x is equal to
If you want to look at the expression, but you know, you'd have to then define what you mean by, at least the way I define things. I don't even know what I mean by normal order of a function of x and y's. Okay? Maybe you can generalize. Probably can, but at the moment I don't want to. Okay? How do you know the normal order things are non-singular? No, you know that because, okay, so let's see. So, well, let's see. Let's use this rule to show that. Okay? Suppose I take f's and g's, and f's and g's are inserted at different points in the field theory. Okay? So what we can do now is completely express everything in terms of normal ordered products with only cross contractions. Cross contractions never produce a singularity because f's are at one point and g's are at another point. So now we have expectation values of normal ordered objects. All expectation values of normal ordered objects, apart from the constant, are 0. So if you take a product of f, what you want to prove?
I am asking a very simple question.
Yes.
If on your two x's,
Yes.
you define normal order,
Yes.
how do you know that quantity does not have any singularity?
How do we know that it doesn't? So that it doesn't have any singularity.
Even when points collide, that you know from equation summation?
When the 2 points collide, when the 2 points collide? Yes. No. I'm trying to answer that. See, all I have to show is that I take arbitrary correlation functions of normal ordered operators. So say I only normal order operators at the same point. You want to ask, your question, if I understood you right, is how do you know it defines a well-defined local operator? How do you know that you can take the limit and not get infinity?
In other words, put one of the x's as z, other one at origin. How do you know this will be an analytic function of z?
Exactly. Analytic, I don't know. At the moment, we've not said anything about analytic. But what I want to show you is that there is no singularity. It's well defined. Right?
Okay.
That as that goes to 0, I don't get infinity. I think that's your question, right? It's a well-defined local operator. Okay? What I need to show for that is to show that if I take correlation functions of normal ordered operators, okay, I take your x at z1, y at z2, whatever, I put them together, but I've normal ordered. I put as many normal ordered operators as I want. As long as the insertions of these different operators at different places, I always get a well-defined result. Nothing blows up. This is what I have to show. Okay? And it's obvious from here.
But then if you have an interactive equation,
Hmm?
and you define the normal order in very exactly the same description, the normal order is this operator minus its 2 points.
Yes.
If I take this definition, it will be in interactive equation, not in a Gaussian case.
Then it will have singularity.
Then it will have
It will have singularity.
somewhere this information about Gaussian is going in, right?
It's going in here. I'm going to use this expression to prove to you that once I've done this normal ordering, I always get finite answers.
So the information about that it's still going in.
Of course.
That's all I want.
Yes.
Information is going in.
It's going in. It's going in very explicit. And because it's all so simple, because it's free, you just explicitly see this. So let me just repeat. Just it's clear to most of you, but let me just say it again. Suppose I take normal order of f and g. We can do this now, f1, f2, f3, it won't make a difference. Let's start with f and g. I take normal order of f and g, and I want to prove that the expectation value of this is well defined as long as f and g are at different points. But what I've done here is re-express that whole thing in terms of normal ordered operators. Okay? But we've already seen that that expectation value of any normal ordered operator, apart from identity, any normal ordered expression in x's, apart from identity, is 0. So this thing here is just lots of factors of contractions, factors of gij, but between distinct points, so that's finite, times 1. And so it's well defined, no singularities. And I'll say something trivial. Let me say it intuitively and it'll be clear. The thing that could have given rise to singularities was self-contractions. And the normal ordering has taken them away.
So in interacting theory,
Yes.
you define your normal ordering of two operators by exactly the same description that you have here. Product of the operators minus this 2-point function.
Yes.
By definition, now you take expectation values.
Yes.
By definition, would it not be?
Yeah, but if you have 2, that probably works. But let's say you have 4. There would be new singularity because 4 are coming together. That is not just product of 2-point functions. Okay, that's the point, right?
So you can have 3 points or 4 points.
Exactly. Because it's Gaussian, all singularities come in pairs.
Yeah, so here you can do it for one definition and that extends to all points.
Exactly.
Which will fail in other cases.
Exactly. So it's a very convenient way of defining operators in a free theory. Okay? But it's crucially tied to being free, as Indranil is saying. If you go away from freedom, you will never use this. You'll use dimensional regularization. Or something like that. You know, some more sophisticated, more usual, more general regulation scheme to define your operators. Okay?
So that you can do here as well.
You can do here, but it's not needed.
It's not needed.
It's not needed, and it's so easy to work with these definitions that it's a nice thing to do. Since a lot of what we're going to be discussing is just free theories, when we can, we'll work with normal order. When we start looking at sigma models and non-trivial manifolds, when the theory will no longer be free, then we will start using more sophisticated regulations.
When people do Sugara construction,
Yes?
then they take stress tensor out of 2 factors of J
Yes?
with the normal ordering.
Ah.
That normal ordering, but this theory is not supposed to be free or any way.
No.
This is the symmetry, but their normal ordering definition is just product of the operators minus the 2-point function.
Yes, their definition is product of operators minus 2-point functions.
Because I'm assuming that action of J on the right one is 0.
Right.
From the operator as I take it. I
Right.
take exactly this.
Right. And that works because you're taking a product of 2.
2-point function. So for 2-point function, this definition is going towards in every part.
Always, yes.
You are going to do something more, you will say.
Yes, if you want 4 your product of 4 operators, you get more sophisticated.
Now it is all clear.
Okay. Excellent. Other questions, comments? Okay. Excellent. So now that we got, so now you know exactly what we mean by talking about normal ordering, right? Every time I say normal ordered operator, you know exactly what I mean. Okay? And every time I do an OPE, all I'm doing is using this theorem, though it's often easier to do it by hand than to use this theorem. Okay? But let's just to show that we can, let's work out one OPE by use of this theorem. Maybe we'll work it out by use of and without use of both. See that we land on our feet. Okay? So suppose yesterday we talked about an operator e to the power I kx. Let's call this k1x. And let's say this is a sigma 1. Okay? And now suppose you've got another operator, normal ordered e to the power I k2x at sigma 2. Suppose I want to work out the operator product expansion of this operator. Okay? I want to work out the operator product expansion of this operator. I'm going to do it using my general formula.
These are prime, you can write down the answer.
These are prime.
Log and
That's right. But yeah, exactly. That becomes a
This
power.
formula will give you the 2-point function itself, which has a log. No?
The 2-point function, which it's yes. So this g's will have a log, and then we'll have to.
There will give you a log, and that becomes a power.
That becomes a power, and that power will of course know about the scaling dimension.
You could have written down because they are primary by.
Exactly right. So let's get the answer and then check it by Indranil's reason. Okay. Of course, there's a number that you wouldn't have been able to get by general reason. Okay. So let's proceed. Okay. So what we're supposed to do is to multiply by this quantity. So we're supposed to multiply by exponential of gij. Now gij is minus alpha prime by 2 log r, log r square. So minus alpha prime by 2 log of x minus x prime square, sigma minus sigma prime square. And we're supposed to sum over all ij, but that's of course integration. So d sigma prime del by del x sigma del by del x sigma prime, okay, and then acting on f and g. But our f here was simply e to the power I k1 x of sigma 1. Now I was supposed to do x's and y's, but I'll just replace this by, what I've done is sigma and sigma prime, because x's act on this and y's act on the other one, so it's convenient to it. So let's call it sigma 1 and sigma 2, e to the power I k2 x of sigma 2. Clear? Okay.
So you have to change the sigma and sigma prime in these properties.
Sigma and sigma prime to sigma 1 and sigma 2. Thank you. Okay. Now, del by del x of sigma 1 produces an ik1. There is an integral over sigma, but it will only click on this. So you can forget about the integral. Right. So that integral was there, but now it clicks here, so we can replace this by ordinary derivative. And this by ordinary derivative, because integral has made it an ordinary derivative. And now this derivative gives ik1, this derivative gives ik2. And so we get exponential of alpha prime by 2, so I have no integral now, alpha prime by 2 k1 k2 log of sigma 1 minus sigma 2, the whole thing square. Now times the product of these two. In the end, we're supposed to set so what we're now supposed to do is Taylor expand and then set sigma 1 equal to sigma 2. So let me just call that. So this times normal ordered e to the power I k x of sigma 1 k1 x of sigma 1 plus I k2 x of sigma 2. What? No, that will be an expectation value.
Yeah. Oh, you are. Sorry. Now it will be non-linear.
Yes. Okay. Now what do we get here? So here I'm going to call this k1 dot k2. Can anyone k1 dot k2 is k1 times k2. But you see, what I will soon generalize to is a theory with many x's. And k1 will be a vector. Many x. K2 is also a vector, and what this will generalize to, we'll get one such factor for each x, and therefore will be the dot product of k1 dot k2. So just to remind us that when we generalize to many x's, I'm going to call that k1 dot k2. For one x, it's just a product.
There's just one zero, and that zero mode is common for all.
Oh, there are as many zero modes as there are x's. There's a zero mode in the x1 direction, x2 direction. There's x1 dot square plus x2 dot square.
All right.
Okay? Now, as Indranil said, we can use this wonderful theorem that exponential of a log is a power. Okay? This 2 cancels that 2. And so we get sigma 1 minus well, let's keep that 2 though. Sigma, because I'll write it as z bar. So z1 minus z2 into z1 bar minus z2 bar times alpha prime k1 dot k2 divided by 2 times normal order of the normal order of just the product. Okay, and now you want to complete finding the OP within the normal order, you Taylor expand. Okay, so let's rewrite what we've got. We found e to the power I k x of sigma 1 times e to the k1 times e to the power I k2 x of sigma 2 was equal to z1 minus z2. I'm not writing the z bars, the same. z1 minus z2 to the power alpha prime k1 dot k2 by 2. Okay, times normal order e to the power I k1 to sigma 1 e to the power I k2 x of sigma 2.
And both of these products on the left hand side are normal order, right?
Yes, thank you. Thank you. And so if I wanted to expand out, let's say the first term, I will set sigma 1 equals sigma 2. So this, if I expand, this will be e to the pi k1 plus k2 x of sigma 2. Then the next term will be the Taylor expansion here. Okay, so the next term will be plus I k1 del x at sigma 2 times e to the power I k1 plus k2 x of sigma 2 times sigma 1 minus sigma times this del will be contracted with the z1 minus z2 del and z1 minus z2 bar del bar.
Could you please repeat the argument that we had made yesterday about allowing classical operations within normal ordering?
You see, what does normal ordering mean? It's just some function. See, now that we understand what normal ordering is, it's totally clear. Because normal ordering gives you just some function, and in that function, you can do classical operations. The reason you couldn't do classical operations without the normal ordering is that your functions were sometimes infinity. Okay? If you tried to do, you would get infinity. But within, that classical operations are allowed is totally clear. It's just, there's nothing to say about it.
Yeah. Yeah, so the other question might have been more pertinent as
That's right.
classical operations
Were not allowed. Yeah. You see, yeah. Actually, I may have said it badly. It wasn't a question of whether classical operations were allowed. Classical operations, in some sense, are always around. But you might be doing classical operations on infinity. Okay. Yeah. There may be a regular. Let's say it again, just to be totally clear. Suppose I have x of sigma 1, x of sigma 2, normal order. Okay. Now, this quantity here is just the same as, this quantity here is just the same as x of sigma 2 plus sigma 2 minus plus sigma 1 minus sigma 2. And so on. Okay, it's just the same thing. As expressions, they're just identical. So there's nothing to say basically. Okay, that classical operations inside normal ordering are allowed. It's totally obvious. Okay. So now what do we have? Let's look at the first term here. The first term is, as Indranil said, just another primary, but with k equals k1 plus k2. So what we've got is this quantity with, so e to the power I k1 x of sigma 1, e to the power I k2 x of sigma 2 is equal to what you would have classically got. E to the power I k1 plus k2 x of sigma 2, as I bring sigma 1 to sigma 2, everywhere there's normal order. Okay. But there's a quantum correction. What is the quantum correction? This is equal to z1 minus z2 to the power alpha prime k1 dot k2 by 2. Okay? And now you can ask, why is there this quantum correction? Well, you see, this is just a general example of an OP. When you have O1, O2 goes to O3, this always comes with z1 minus z2 to the power h1 plus h2 minus h3. Okay? But we found yesterday that h was equal to alpha prime by 4 k square. So h1 plus h2 minus h3, h1 plus h2 minus h3 is equal to alpha prime by 4 into k1 square plus k2 square minus k1 plus k2, the whole thing square. Because h3 is k1 plus k2. Which is equal to alpha prime by 4 into alpha prime by 2 minus alpha prime by 2, k1 dot k2. And therefore you get z1 minus z2 to the power alpha prime k1 dot k2 by 2. And the minus has gone because it comes in the numerator.
The 2-point function in
Only when k1 plus k2 is equal to 0, because this would also have worked when k1 minus k2 is equal. I mean, there's a degeneracy. K and minus k have the same dimension, but the 2-point function will only work when k1 is at minus k2.
Yes, because right hand side you want identity.
Because yes, exactly. Sorry, you're right. Right hand side you want identity. Exactly right. Only when k1 plus k2 is equal. Absolutely right. Excellent. Okay, so this OP is something we want to remember. We will use repeatedly. This OP is something we'll use repeatedly. If we have an e to the pi kx and another e to the pi kx, you get what you naively have got, dressed by a power. As in reply to Indranil's question yesterday, the power goes to 0 in the classical limit, alpha prime goes to 0.
That is what you are saying,
Quantum,
quantum.
yes, exactly. Exactly. And so everyone's happy, everything is good. Any questions or comments? Yes. What? Why not? Where? Here? Oh, I'm sorry. I had a sigma 1 minus sigma 2 square. I wrote that as z1 minus z2 times z1 bar minus z2 bar. Okay? So everywhere I also have a z1 bar minus z2 bar to the same bar. I just haven't written that. Okay, it's the usual thing. I just don't write the bars, just to save on writing. Okay? Just that. Nothing. Okay, great. And now I think we're really done. I think that's everything I wanted to say about these conformal field theorems in general, and about one or two last comments. Firstly, last class or maybe the class before that, you might remember that we derived the dependence of the partition function on the metric of the manifold that we're working.
Conformal.
Yes, we got the answer that it was C by 12 or C by something times r 1 by box r, or del phi the whole thing square. Now this argument already tells us something quite cute. It tells us that it's not possible to define a diffeomorphically invariant conformal field theory unless C is equal to C bar. So what do I mean? You know, your question reminded me of this. All through the course I keep pretending like there's no anti-holomorphic anything. But of course it's there. Everything goes along for the ride, but you have to be a bit cautious in that. For instance, what is there to stop a theory from having one value of C in the TTOP and another value of C in the T bar OP? And such theories are easy to write down, at least naively. A chiral fermion will do, as we will see. Okay? However, now we're going to run into a problem. Because let's use...
The partition function will not be invariant as the diffeomorphism will scale the matrix.
Yeah, let's use the analytic dependence to find the analytic thing, as we did, to find the dependence of the partition function on the metric. We get that it depends on the metric through C by 2, C by 12 or whatever, times some known factor. But the same argument from the anti-analytic side will give you the same answer, except C will be replaced by C bar. If C is equal to C bar, everything's good. But if C is not equal to C bar, how can both be true? Something must give. And the thing that gives is that it's not possible to regulate this theory in a way that preserves diffeomorphism. Okay? So these theories with C not equal to C bar are bad in the sense of putting them on arbitrary manifolds and preserving diffeomorphism. You can't, as usual with anomalies, it's possible to switch around where the badness goes. But you'll never get everything good in these theories. And most simply, they will have a diffeomorphism. Okay, is this clear? No, I mean I have a dependence which is C by 12 times R. Another derivation gives C bar by 12 times R. So C must be equal to C bar. So what minus is?
You want to cancel it or not?
No. At the moment there's no cancellation. I'm just saying that the left central charge and the right central charge have to be equal to each other.
To be consistent that in both cases you get the right answer, same answer.
Same answer.
But it's okay for your partition function to change from one manifold to other manifold by scaling. That's what you're saying.
It's okay in a general conformal field theory. That's a fact of life. You take the Ising model, two-dimensional Ising model, or the free boson theory, partition functions do change. As long as you've got a well-defined rule for how they change under wild transformations.
It's just the well-definedness claims that C equal to C.
Exactly. The fact that you've got an answer, you don't have a contradiction. Yes, gives you C equals C bar. We will soon want to cancel in string theory. But that's another matter. So far we've just been studying conformal field. Okay. Okay. I think that's all I want to say at this point in our discussion on general conformal field theories.
Why if you want to get rid of this wild anomaly,
Yes.
if you want your partition function not to change under this,
Yes.
this area, then you will say that they have to.
Then C has to be Z. C has to be equal to C bar. Is that C equal to C bar? C only. Yes. Yes.
What was the relationship between C and R? Sort of looks like an Einstein equation, but
Between what and R?
root B scalar and stress tensor.
Well,
But it's controlled by this conformal function.
are you saying that the dependence of the action on R?
You basically have that the principal stress tensor will be something.
Yes. Yes.
It sort of looks like the Einstein equation.
Oh.
I mean, because again, you're getting dependence on the stress and the tensor of your manifold. My question is sort of why is it being controlled by this conformal term? Why would knowing how conformal it is
Yeah. Stress tensor is equal to R. Yeah. Well, there are many things to say. Firstly, the metric is not a dynamical field in what we're doing. Einstein's equations, the metric is a variable of your problem. Here we fix the metric once and for all, and we're finding that the trace of the stress tensor is equal to R. You know, the way you should think of this, though I admit that it looks little.
So it's like if you had
What
space
is
on
intuition
government
by
back.
changing the metric? It's like sort of an intuition of motion by changing the metric. You went little bit away from flat space, that is by changing the metric. So this is sort of an intuition of motion for the metric.
Not an equation of motion.
I mean, just imagine you have some energy density. Imagine you have an Einstein space-time. There's no matter, there's nothing in there, but you just have like some dark energy or something that was causing a stress energy tensor.
Yes.
That's and this is sort of us working backwards, saying that if you see curvature, this curvature of energy density is even though we're not space-time.
Even though we're not treating the metric as dynamical, that's a very important point. You see, what this is saying is that the stress tensor, one part of the stress tensor is completely determined by it's a deformation of the statement that the stress tensor was just 0, classically. Okay? Now the stress tensor is not 0, the trace of the stress tensor, but it's determined by what your manifold is doing. You know, I don't think of it as R being determined by T, rather the other way around, because we're just doing conformal field, quantum field theory. I give you the manifold, and then I ask you, what is the stress tensor on this manifold, the trace of it? And you would naively have said, well, the trace of the stress tensor was 0. That didn't bother you. Now we're deforming this relationship, not being 0, but being determined by what the local geometry is doing. It is true that it's looking a little like Einstein's equation, but I wonder if there's some... let me say one more thing. Okay, suppose I took matter along the lines of what Indranil wanted maybe. Suppose I took, I could do the following. I could take matter, get a conformal field theory with some matter, and then integrate out the matter, and then do a path integral over the matter. Suppose I wanted to do that. So we've so far been treating the metric as fixed. But you may be asking, suppose I now allow the metric to become dynamic. What this is telling us is that we know what the action for that metric is. Okay? That action for that metric is not square root gr. And that's sort of nice, because in 2 dimensions, square root gr is topological. It has no dynamics. Okay? Instead, it's this R, 1 by box R, which is not topological. Okay? And Advait knows all about it, so I'll refer you to it to hear more about it. It's related to this thing people call a Liouville action. Okay? So, this is a game that people have played. Get induced gravitational dynamics by integrating out conformal matter. And it's an interesting game. Okay, it's not exactly your question. I don't exactly know what to say about the question. Sorry, I changed. Okay. Okay, excellent. Shall we continue? Okay, so now we're on masters of conformal field theory. Right? The only things you guys don't know that people know about 2-dimensional conformal field theory is about Wesso-Witten theories, about minimal models, about... There's lots you don't know, that's okay. I will, but when we get to it. Right. But now the structures of the theory, the main ideas, actually there's one main idea that I've not really focused on, which is null states, which we will come to at some point, but it's a very key idea in conformal field theory. We will come to that. That I have not at this stage of our discussion posed. Okay, that's one key idea that I've not. But anyway, you know a lot about this 2-dimensional conformal field theory now. We've seen the Virasoro algebra, we've seen these contour integrals, we've seen analyticity all over the place. We've got these representations, these Verma modules, primary operators, OPs. Okay, we're a state operator map. We're quite good, right? We're ready to fly. So now let's try. Now we want to get back to what we really started out trying to do before we got waylaid by all these technicalities. What we really wanted to do, if you remember, was to study the dynamics of a string. And the dynamics of the string was determined by a number go-to type action, exponential of minus 1 by 2 pi alpha prime square root det of del alpha x I del beta x. I've shamelessly moved to Euclidean space at this point. At some point I will give you a careful analysis of the analytic continuation between Lorentzian and Euclidean space. But at the moment, let's shamelessly move to Euclidean space and let's hope that there's no issues. Okay. Everything that we did goes through. Everything that we did is going from this to the Polyakov action, of course, works also in Euclidean space. Analytic continuation of what we did. In 2 dimensions is always possible. Always possible. Because it's so simple. There's no analog of this Weil factor problem. This conformal factor problem. Okay? I will show this to you at some point. Very careful. In this case, it's not blah blah blah. You can actually see it. Okay? The question is it always possible to analytically continue the Einstein path integral? There are many questions about that in 4 dimensions. Okay, people do it all the time. Certainly some truth to it. Euclidean quantum gravity is much used, much loved, much, gives results that are consistent with other ways of thinking, at least in perturbation theory. However, there are many issues with it. The single most irritating issue is this thing about the conformal factor. Have you guys encountered it? The issue is this, that there is in Euclidean, the whole point of going to Euclidean space is that it's an analytic continuation that makes your path integral better defined. Okay, a path integral that was oscillating turns into a path integral that at infinity decays. That is the whole point of it. Okay, and we see that very clearly with the scalar action. We have del phi the whole thing squared, which e to the power I del phi the whole thing squared goes to e to the power minus del phi, Euclidean del phi, positive definite del phi, the whole thing squared. Any field that oscillates at all is damped. Fast oscillations are very fast damped. Put a v of phi, any field that goes up to infinity is also very fast damped. They're really good. That is the whole point. Some analytic continuation that gives clear meaning to your Lorentzian path integral, and then when you finally want Lorentzian answers, you analytically continue back as carefully as you can. The problem with the Einstein, the Euclidean Einstein action is that it's not positive. Have you guys encountered this ever? In 4 dimensions, the Euclidean Einstein action is not positive. There is a scalar associated with basically Weil transformations. Take a metric Weil.
Oh, it's clearly seen because R minus del phi is
Right, exactly.
and minus is the
Exactly. Okay, so when people, mostly what people do with Euclidean quantum gravity is just do classical stuff, and you don't care. When they do one loop stuff, they tie themselves in knots. And people get different answers and they debate about it. They talk about some analytic continuation of this mode and how it's consistent with diffeomorphism invariance. It's a thorny issue. There's a lot of issues. Okay, in 2 dimensions, none of this is at all. In 2 dimensions, basically because that Weil factor is not there. Yeah. So in our case, we are really a solid ground. We know how to do this very clearly. It's as good as analytically continuing quantum mechanics. In quantum mechanics, there are no issues. I'll carefully discuss it. Okay? So, fine. So what we have here is now this Polyakov action. So we will replace this by dx, dg, exponential of minus 1 by 4 pi alpha prime, g square root g alpha beta del alpha x mu del beta x mu. This is the path integral we want to calculate. Now, let's think a little bit. Now we're going to, our job is going to be how to discuss how to compute this path integral. Okay. But before we do that, I'm going to give you 5 minutes about what we're going to calculate with this path. You see, we've already talked about how little loops of this thing give you a string. Now we have quite good understanding of this whole thing for these little loops. Right? You know, when we take a little loop here, it's got some vibration modes. These are the modes. We solved the equations of motion classically. These are the various vibration modes, each of which is a particle described by Schrodinger equation. Okay? Now, see, so what are we going to be interested in calculating? The thing that worldsheet string theory, the thing that I'm trying to teach you about, is built to do is to compute scattering amplitudes. Okay? So the thing that we're going to do is this. Suppose we've got a string in a particular oscillator state. Go on.
So, can we write down Schrodinger equation in your space-time?
Yes.
What I mean is that the time evolution that will be consistent will be one thing. You have states, you have few states in all states, you can define states, you
Yes.
have everything in all states.
Yes.
You know how time translation works there.
Yes.
Is it equivalent to writing down a local Hamiltonian in the space-time?
No, but we know what to do. Let us remember how we got our Schrodinger equation in space-time. For each particle, we got it from the constraint equations. Do you remember?
Yes.
Okay? So it's not like the time evolution on the world sheet will correspond to evolution in space-time. It's the constraint equations of the world sheet that give you evolution in space-time. Do you remember? Let me remind you. How did we proceed? How did we do our quantization? Okay? You see, time evolution in some sense was always a fake because of diffeomorphism on the world sheet. Okay? It looks like it's not a fake because we fix gauge.
Yes.
But then after we fix gauge, we're supposed to impose the constraints that we lost because we fixed gauge. That t is equal to t bar is equal to 0 constraint is what gives us time evolution. Okay? So you can write down time evolution in space-time. But that's not obviously tied to what the ungauged fixed, the see, let me say it again. If we just take this X theory and don't impose the constraints, then there's a great deal of dynamics on the world sheet that has nothing to do with space-time physics. It's the constraints, the t is equal to t bar is equal to 0, that plays the crucial role in getting dynamics in space-time. Okay, so just Hamiltonian evolution of just this free boson theory has very little to do with what's going on in space-time. Then it will work.
Then the time evolution that we get from world sheet.
Yes, will be basically same as space-time evolution.
With the local Hamiltonian.
With some Hamiltonian, of course, this will be time evolution of what the string is doing. Yeah, but yes, basically right. If you want to keep track of the motion, the shape of the string in space-time, the world sheet Hamiltonian will do that.
And that Hamiltonian will be local.
It will be local on the world sheet, but that is same as local in space-time because you fixed. Let's say you fix sigma is equal to x1 and tau is equal to t. Yeah. Yes.
Scaling operator,
Mhm.
and your space-time Hamiltonian is basically a combination of that.
In the gauge that you're working,
In the gauge you're working with.
that you are working. But we're not going to be working that gauge. We're going to this nice Lorentz invariant gauge. Okay, and there, all of the dynamics in space-time comes from the physical state condition, from the T is equal to T bar is equal to 0. So there's dynamics of the conformal field theory which has essentially nothing to do with what's going on in space-time, as we saw when we quantized this. Okay, because that's dynamics under a fake time in our gauge. Okay, great. Great. So let's keep going. So what are we interested in calculating? What we are interested in is one state of free string theory, another state of free string theory, coming, banging into each other to produce more things. That's what scattering is. Okay. Now, what does a state of free string theory look like? It looks like a little tube coming in from infinity and then stuff happening here, vibrating, doing whatever, according to the free equation. Another state's coming in, it looks like another little tube. And now these things are supposed to bang into each other to produce, to scatter. Now let's remind ourselves how, when we did Feynman diagrams, how Feynman thought of this problem. Feynman thought this way. He thought, okay, we should sum over all ways of the particle going from early times to the time where it's going to scatter. Sum over all ways of this particle going, then they meet, and something singular happens. These two particles maybe turn into one, which at another point something else singular happens and does something like this. Each of these represents free propagation from here to here, from here to here, from there to there. And then something else happens. That's not free propagation. Something that on the world line is clearly a singular thing. Everywhere else on the world line we've got a one-dimensional manifold. This joining point is not. It's clearly something singular is happening. And I have to give you the rule for what singular thing is happening here. And that rule we get out of local Lagrangians or whatever, some way. That's the way Feynman thought of scattering in world line notation for particles. Now, you might think it's going to be something similar. We've got these tubes, these other tubes, they're going to bang. We're going to have to specify some rules for what happens when they bang. And so, knowing what the string did freely, which was like knowing what the free particle did in the first part of the course, first lecture or two of the course, it's not good enough. We're going to have to specify rules for interaction. This is, the interesting thing about string theory as we understand it today is that is not the case. And in order to understand this, look at this. Suppose we had this happening.
Another closed thing.
Yeah. Suppose you have, something like these pants going to my arms. These are the two strings. They're going, they've joined up, and now they're going whoosh. Nowhere along the way is there anything. Okay, in this case, if I stitch my t-shirt to my pant, then nowhere along the way would there be anything special about this manifold. We can smoothly have this evolve to this, where at no point on this on this two-dimensional manifold could you point to it and say, this is a special part. Very unlike what's happening for the particle.
It will not happen in any dimension, except in one dimension, I think. No?
Well,
The dimension of the manifold will be big. In one dimension it becomes bigger.
there are other bad things that happen in high dimension. Okay, and this has to do with the fact that that you can have okay, yeah. People have tried very hard to make sense of this for 2 dimensions, 2 plus 1 dimensions. It doesn't work for a variety of reasons. Okay, we'll leave it at that. So something like this should work, because weakly interacting D branes, let's say 3 plus 1 dimension, D3 branes as probes exist in ADS. So there is a weakly interacting theory of these things. Nobody's ever managed to work it out. It's actually a very interesting question. Okay, it's something I've tried actually, which I'm telling you, we never succeeded. But it's a very interesting question, not a stupid question, but it's not a trivial question. It's hard. Okay, yeah.
And so far from what we've done, there's nothing that told me that, for example, I can have this self-intercept.
What do you mean by self?
Have this world self-intercept.
Let's say it's self-intersects. Let's say so.
No, I'm saying that you're back having to, right, it's seemingly the allowable thing allowed to be allowed.
Something like this. You want something like this to happen?
No. As sort of.
Oh, you want not a manifold.
Yes.
You want not a manifold.
I'm saying
Okay.
there's nothing in the rules over here that told me that avoid all singularities.
Yeah. So if you were to
Conversely, if I am to take a sum over all paths, I could get to a lot of bizarre things that wouldn't show up for like the two isolated one paths.
yes, that's a logical possibility. It's a logical possibility that in order to, make sense of your theory, you will need to do things other than this. Surely you have to include this. Okay? Now we're going to go with the flow and hope that we land on our feet without having to fix things up. We just do this and see whether things work nicely. Surely that's the most beautiful thing to do. Okay? Let me say it in another way. If we sum over all manifolds, we get non-smooth manifolds as a limit of smooth manifolds. We're going to do path integral over all manifolds. If the path integral automatically highly suppresses non-smoothness, then we're done.
Just intuitively, just in
Yes.
the Simon diagram kind of picture.
Yes.
The singularities, I know exactly where they are, what they're coming from. It just seems like with two-dimensional materials, there's so much more that can go wrong.
There's so much more that can go wrong. Let's see. Let's start as follows. See, firstly, with one-dimensional manifolds, there's no way these things interact without singularities. Here you can have interactions without singularities, as we've just seen. Okay? So there are many smooth manifolds that give rise to interactions. Okay? Now, we're going to make the postulate. Okay? That our scattering is entirely given by these things. Let's see what. Now, but of course we're going to sum over all possible manifolds in the middle.
You think that when you're computing scattering, you look at like 2 or 1, there's really nothing. Like in perturbation theory, there's nothing really going there.
That you're allowing for things to go singular, because you will sum over everything, but it will not happen. It's very much like in quantum field theory. You sum over all field configurations, but non-smooth field configurations are very highly suppressed. Okay? Now, this is not a complete answer, because there could have been special enhancement factors of the right rules that single out. But let's go with, we're just trying to build a theory, right? We do the simplest thing and we see. As you will see.
Take string coupling to 0.
Yes.
Do we expect the manifold to become singular because naively one might expect it to reduce to just ordinary Feynman diagram?
As we take the string coupling to 0? No. You see, even in classical string theory, okay, we interchange arbitrarily many highly excited states. And that sum over excitations of all those very highly excited states is captured by floppy manifolds.
Right?
By these floppy manifolds. Okay? So even in, it's true that it reduces to Feynman diagrams, but Feynman diagrams for a theory with an infinite number of particles and very particular coupling constants between them. And that whole thing is captured by this structure.
Very non-smooth field configurations are updated because of kinetic term.
Because of kinetic.
So we need a kinetic term or metric in updation.
We don't need a kinetic term for the metric, because the metric can be gauge fixed to 1.
It's something which knows about the non-smoothness of the manifold.
No, but listen, why do we, non-smoothness of the manifold. You see, this manifold, this metric here, really what is important is the non-smoothness of the manifold embedding in space-time. The metric of the world sheet was a fake. Really what you are summing over is embeddings in space-time of two-dimensional surface. It's those that should not become smooth, should not become non-smooth, and this is controlling that. This is the action that controls the maps from two-dimensional surfaces to space time.
How does one state the similarities in Feynman diagrams in some quantitative or at least in a mathematical way?
Or we just declare we're only going to sum over smooth manifolds.
I mean, as it's probably obvious that the Feynman diagrams, they're non-Hausdorff manifolds or something. I mean,
I don't even know. all that. Here we're just going to declare. We sum over. What we will see is that in appropriate limits, you will reproduce the physics of Feynman. These appropriate limits will be like low energy limits. When you will reproduce the results of Feynman diagrams with only a finite number of fields. Because you remember that all the infinite many fields of string theory have increasingly high mass. So if you go to low energies, you should see gravity coming out, for instance. We will see this work. Okay? So we won't get some crazy stuff. Okay? But let us proceed. Let us try. You see, when something very beautiful occurs, there's always the possibility that eventually it will get contaminated. But one should hope, right? This is part of the reason we do physics, is that we hope that the truth is beautiful. So the possibility that something very beautiful, let's try to make that work before trying to put ugly features in it. Okay? And you should, I mean, we can be skeptical, but you must see that this is a very beautiful replacement for an ugly formula, for an ugly structure. The Feynman diagram structure was in the end quite ugly because of these points. Because there was lots of arbitrariness in what to do at those points. The vertex factors could have been those of gauge theory, of gravity, of scalars. There's lots you could do. I'll just say one thing and then back to you. What is really interesting about this is that if we adopt this rule, then precisely the same dynamics that governs free propagation also governs interaction. Because the motion of this world sheet is local. So whether it's locally propagating here or here, you cannot tell the difference. The locality of this world sheet theory tells you, and our hopeful rule, we only keep smooth stuff, tells us that there is nothing new we have to do in order to get interactions in string theory. Once we understand how to make string theory, free string theory, we get interacting string theory almost, we'll see to what extent, free. This is an enormously beautiful idea, and one we should try to pursue. Yes?
So, obviously, the manifold in and of itself looks very non-singular. But let's say we just look at constant time slices.
Right.
Then at one point, we before and after that one instant, we have, let's say, two
Excellent.
strings, and we have one string afterwards.
Excellent.
So that
Yes.
looks like something non-singular.
Non-singular happening. But you know, if I do this time slicing at different times, I do this slicing, where the singularity first occurs will be different if I do this.
Yeah.
It's clear that there's no fundamental significance to that, at least in Euclidean physics. Right? It's like these pans. You slice them in different ways. At some point on slicing, you will see 2 going to 1. But it's slicing dependent, and it's totally clear from a higher view that that is not a very fundamental thing.
So that has to happen. You started off with an electron and a positron. You ended up with a photon. There's no singularity in the equation.
There's just no singularity in the equations, and there's no point along which you can identify and say this was where the change happened. Unlike in a Feynman diagram. Yes.
Then we just follow it. We go for this. Then we will get this kind of pattern.
Yeah, so I'll explain exactly what in a minute, what mathematical formalism is. So let's get to that. Now, this looks like very nice, but there is this one ugly thing. and that is these tubes. For scattering, these tubes go off to infinity, and we have to do these sums over tubes. Now, this is what Feynman gave propagators. Okay? And that's okay, but we're not trying to split up the diagram into propagators and interactions. That's, by the way, what string field theory people do. This is what makes string field theory so ugly. Okay, it's very useful, as Ashok has shown us now, beating all expectations that it was nonsense. But it's very ugly, in my opinion.
So, in that way, we won't be talking about ace matrices in this theory of some asymptotic union.
Yeah, but let's see. This is what we want, but this is physically what we want.
Yeah.
Now what we're going to do is to try to find a mathematical replacement for these tubes. And to do that, what we're going to use is the state operator. You see, suppose we've got this long tube here. If we can do, let's remember that in conformal field theory, a tube like this is conformally equivalent to the disk. I'm not saying to all of the sphere, because I'm ending this tube at some point. So let me be here. I've got this sphere, and I'm joining tubes to it. These tubes go off to infinity. But by the same map that we use, this Z versus W map, we'll turn the half cylinder into a disk. However, there is something interesting. And that interesting thing is the following. Okay? That interesting thing is that along the disk, we didn't have the vacuum. We had a particular state, the state that we wanted to propagate. But we know what to do. We know what happens to this map with states. We get the state operator map. Okay? So, this intuition suggests that instead of this picture, since we don't want to talk about the stuff, that we'll replace it by this. Instead of these long tubes, we will replace these long tubes by an insertion of a vertex operator. That plays the role of the state along the long tube going to infinity.
So this is some n-sheeted Riemann surface?
N-sheeted Riemann surface. At the moment I've drawn a sphere, but as you said, there's no particular reason why these tubes have to attach to a sphere. We just want smooth manifold. So we could have had a torus. Okay? Now you can ask, which vertex operators should be put? Well, that corresponds to which states are propagated. Sure. We can put any operators that correspond to free solutions of string theory. We have already got a rough appreciation of what the free solutions of string theory are from the first part of our course.
But you have to put the vertex operator.
You have to put the vertex operator, but remember that it's not anything goes. If you put a particular oscillator, then you have to put an e to the power ikx with k squared is equal to m squared by the formula that we derived earlier. Okay? So there's some restriction. We'll see this in much more sophisticated way very soon. You have to put not, so what I'm saying is not any vertex operator. We will see how that comes about. Okay. Which one?
Putting the
Vertex operator? Yeah. See.
What vertex operators essentially?
Yeah. What are vertex operators? Vertex operators are just operators, local operators. Okay? Now, let's remember that in the first part of the course, we derived what the spectrum of string theory was. For each one of the 24 oscillator states and a particular momentum, subject to Marshall condition, we had an allowed state of the theory. Okay? So, these operators will be whatever the operators are dual to those states. We're going to do this a little more sophisticatedly, but that's roughly the idea. Okay, so it's going to be some operators which are dual to oscillator states of string theory. We've spent the last 2 lectures developing those, right? Del x will be an operator like that. Times e to the power ik dot x. because that's the thing that gives it momentum. But it won't be arbitrary, because del x times e to the pi k dot x, you'll have to obey a Marshall condition. You remember that t is equal to t bar is equal to 0. First, k squared was equal to m squared, where m squared was determined by the oscillator constant. Okay, so there will be some restriction. We will rewrite these restrictions from our new point of view. But you already see that that's what you should expect. Okay? So there will be vertex operators, but not arbitrary. Vertex are just local operators.
So, in terms of some particular string diagram, what do these vertex operators, what would this correspond to? And would this correspond to some...
This guy going off to infinity.
Hmm?
The state created by the operator going off to infinity. So it would correspond to what you expect for the world sheet of an S matrix. What?
What does an interaction look like?
This is the interaction. You see, each of these x's is the tube going off to infinity. So imagine doing this. Replace this by disk. And do the conformal transformation in this part of the disk. Similarly here, here and here. So what's left behind, I mean, it's all mixed up. The propagation and the interaction are all taking place together.
This diagram is
Same as that diagram. This is the diagram we will actually compute.
and the second piece means you have a
Yes, now we are supposed to sum over all possibilities, right? We said all smooth manifolds, so we should sum over this, we should sum over. No, you cannot. You cannot. And we will explain why not. Okay, only primaries will work.
So the second one is a one loop diagram in some
Exactly.
Feynman language.
The Feynman language is a one loop diagram, this is a two loop diagram. Exactly right.
in this diagram it means you have a hole inside this.
In this diagram it means you have a hole inside this, exactly. Okay? The reason we cannot take secondaries is associated with the fact that you see, when we worked out our state content, we did this additional gauge fixing of going from 26 to 24 dimensions. And then we had arbitrary oscillators. Here we've got 26 x's. So in order to match all oscillators 24, surely there must be more restrictions. We're doing a different gauge fixing. So we'll understand that as well. Okay, other questions or comments? Okay, next question is, where should we insert these operators? Well, let us remember that the positions before we do any world sheet gauge fixing were totally fake. There was diffeomorphism invariance. Clearly what we're supposed to do is to integrate over all possible insertions. This also follows from here. This thing could have joined here or here or here or here, all over the place. First we're supposed to integrate over all embeddings, and within any given embedding we're supposed to integrate positions of vertex operators everywhere. Okay? So we already understand the thing that we're trying to compute. We're trying to compute path integrals over all embeddings together with insertions of vertex operators, local operators. Path integrals over all embeddings together with insertions of local operators, okay, together with insertions of local operators, and the result for that we will identify with the S matrix of string theory with a little tune. Okay, so our job now is to understand how to compute this path integral.
No interaction is also a possibility.
No interaction is also a possibility, though as usual you see, no interaction just in flat space will give you the vacuum energy of flat space. Okay, so that's observable in a sense. No interaction on the sphere would give you, is like the tree-level vacuum energy of string theory. No interactions with the torus will give you the one-loop vacuum energy of string theory.
By no interaction I am just saying that these two.
That is of course always possible. Yeah.
What you were saying
I was talking, sorry, I thought you meant no vertex operators.
no interaction seems like two spheres.
Two spheres, that's also fine. Yeah, things can This is the non-connected part. Yeah.
So in regular quantum field theory, if you were given a kind of Feynman diagram, that you'd have like S channels and P channels and U channels.
Yeah, and there's not but now you suddenly get certain, like all,
Yeah, the
there's
STU
permutations on this here, so it's very confusing to you.
Exactly. And this is one of the beautiful things about string theory. One of the beautiful things about string theory is this, that if you, we will say all this, but if you take this object, let's say on the sphere, and you rewrite it in terms of propagator exchange with in the S channel, an expression with just propagator exchange in the S channel reproduces the full answer. However, an expression with just propagator exchange in the P channel also replaces the full answer. Well, the full sum is not different. Okay, it's very similar. We'll even give an argument for why there had to be some energy restriction. Very similar to what you see crossing symmetry in conformal field theory.
This is 4-point function of primaries on a sphere.
This is 4-point functions of primaries on a sphere, except that we have to now integrate over the positions of these insertions. Okay.
So now put some gauge index on it.
Gauge index on X. Well, we are going to allow for ends of, at some point we'll allow for open strings, and when you've got an open string, we'll allow for
Chan
pattern factors. So basically degrees of freedom and the boundaries of open strings. Is that the- You know, you want to define a conformal field theory. Typically it would, because you need to give the gauge field some interaction.
You are not getting the global function. This is a global function. This right now, the x's that you have, they only have one kind of global function, Lorentz transform operator.
Good, good,
This is your index.
good.
Now you can put another index, a index.
Oh, you want to make more x's.
You make more x's, and you give some global symmetry.
Yes, okay.
That is totally fine.
This is fine. Okay, please go on. But let me tell you what we will eventually conclude. Though we are building this all up with the free boson, we will find that the mathematical structures we construct will work when we replace this by any two-dimensional conformal field theory with certain properties. Okay? So in the end, what we're doing is, you know, the space of classical solutions of string theory are two-dimensional conformal field theories with certain properties. And two-dimensional conformal field theories come in all spaces and sizes and so on. It will include the kinds of things you're talking about, such as Westerbein-Witten modulus. Okay? But with certain properties. So it will eventually work. Okay? But right now, let's stick to this, because we will be led to the rules by analyzing one model in detail. Once we understand this one model, we'll easily be able to generalize.
The picture of the closed string that we had discussed earlier on this course,
Yes.
they have included at first the tachyon and then some scalars and also a photon, right?
No, a photon on one side, a graviton.
Okay. So there's no photon in the
There's no
closed
photon in this case.
spectrum. So there's apart from if the graviton, there's no other gauge field.
Well, there's a B mu nu field,
Oh, the two.
the two form. There was a dilaton, B mu nu, and graviton at massless level. Okay. Now, when we generalize this to the superstring, as I will try, we have a quick discussion of the bosonic string, and I will try to invert the order of Kolchinsky and immediately discuss also the superstring after that. There will be some, in one case, in type 2A theory, we will also have photons from what's called the Ramond-Ramond sector. We'll see. Yes. Or even just plain Westerbein-Witten model.
I was adding one more gauge field.
Okay. What gauge field coupling to what? So you want a coset model? Sure. So, yeah. So fine. Any two-dimensional conformal field theory satisfying certain properties will work. But please go.
So the gauge field universal model, the process model, that gauge field will not have a space-time index, right?
That gauge field will not have a space-time index, no.
So I was going to use the space-time index. All I'm saying that can you get some other gauge field in your game by doing some gauge field?
Are we talking about a space-time gauge field or a world sheet gauge field?
Worldsheet, I want to put things on worldsheet so that I get an extra gauge field out of space-time.
I want to get extra gauge fields in space-time. Okay, good. Yeah. So what you're groping towards in the end is a compactification. Okay. You see, and as I said, we will find the final statement will be the space of conformal field theories with certain properties. Now, one possibility for conformal field theory is R4, just a sigma model on R4, times something else in some compact space. That something else in some compact space could be something with isometries that will lead by Kaluza-Klein reduction to gauge field. It could be something more sophisticated that will also lead to gauge field. Could be a Calabi-Yau manifold. I mean, all kinds of things can and will happen. Okay? But let us first look at the simplest model. Okay. Any more questions? Okay, excellent. So now you guys are all convinced that what we want to do is this path integral with insertions. Okay? Now we just have to figure out how to do this path integral. We sort of convinced we can, right? Because we could solve the theory classically. So surely, if you can do it classically, how hard could it be? Okay? Well, let's do it and do it carefully. Fine. So we'll rewrite the path integral we want to compute. We want dx, dg, okay, exponential of integral square root g alpha beta del alpha x del beta x mu minus 1 by 2 pi 4 pi alpha. Now, before we start, there are a few things just to keep in mind. The first is that though we're writing it in this language, because we've seen from experience it's much easier to write it in that language than in this language, this is going to be the definition of our theorem. We want to remember that what we had in mind was doing something like this. Okay? All that I'm going to use of that statement is the following. As you remember from the earlier part of our course, the relationship between this and this was a complicated relationship. It was not straightforward. It was one of equivalence classes. You remember that for every solution here, there were an infinite number of solutions of this action. That is, while equivalent on the world sheet. Okay? And doing the path integral over this is plausibly the same as doing the path integral over this, only because the while factor, classically, did not enter the path integral. Changing the while factor was a symmetry. Because all different while factors correspond to the same solution. So you shouldn't get different answer for the action depending on what your while factor was. This we're going to take very seriously. This feature of the classical problem we will take very seriously. We want to do a quantization of this that will treat while transformations as a gauge symmetry. Because we want to treat different field configurations that differ by while transformations here as the same physical configuration. We want to be doing the sum over embeddings of x into space-time, not something else. Okay? We want to treat while transformations as a gauge symmetry. And this already is puzzling from what we've already seen. Please.
This lesson on all manifolds
Yes.
is implied by this dx integral.
This in a summation over all manifolds is implied by the dx.
Can take any value.
X can take any values. That dynamics will tell us. It's like in a field theory. You are doing an integral over d phi, dx, d pi to the 4. How can you be sure it's smooth? Well, dynamics ensures, suppresses smooth, unsmooth configuration. Exactly, so what's the deal? As we discussed in great detail, each X boson carries central charge 1. We've already seen evidence that there are going to be 26 X's. We'll have central charge 26, and deep theorem of mathematics, the 26 is not equal to 0. So how is it going to work that this thing is going to be invariant? So it looks like it's not going to work. But before we rush to judgment, let us try to do it more carefully and see. What have we not done more carefully? What we've not done more carefully is the integral over the metric. In our crude analysis of the problem, we just gauge fix the metric set to 1. But now we're doing a path integral. Let's do it by the rules of path integrals. So what are our rules? 1. Diff is gauge. World sheet diffeomorphisms are gauge. That of course is obvious. 2. While is gauge. So what we have is the path integral of a gauge theory, where the gauge invariance is world sheet diffeomorphisms and world sheet while transformations. Okay? We want to now do this path integral, and we're going to use the trick that physicists always use in dealing with gauge theories, namely fixed gauge. Fixed gauge, and we use Faddeev-Popov. But the point is, the first point to note is that we have exactly enough invariance to fix the gauge to a standard metric. More precisely, we will see that depending on the topology of our manifold, okay? Yeah, there are a finite number of parameters. Okay? The space of all metrics, it's just a mathematical fact I'm telling you about now, and we will derive as we go along, that there is the space of all metrics. So suppose we've got a genus G manifold. So do you understand what genus is? Sphere is genus 0, torus is genus 1. The number of holes you eat out of your donut is the genus. So you've got a sphere, then you eat out a hole, you get a torus. Eat out another hole, you get a figure 8 shape, it's genus 2, and so on. Okay? And yeah. So the number of parameters we will have to fix. So first I'm quoting a mathematical theorem, which we will prove as we go along. That is that, suppose I've got a genus G manifold. Every genus G manifold is while equivalent, while and diffeomorphism equivalent to a standard class of genus G manifolds, okay, labeled by 2G minus 2 is this right? 2G minus 2, just it. Yeah, this torus is actually exceptional. There's an index theorem which relates the torus has both. Torus, this case,
Age, right? G and age.
yeah, I think it's 2G. I'll check this. I may have got some factor of 2 wrong. What? This is the Euler character. Yes, yes. And I think that I may have got some factor wrong. I'll check. But some number. Okay, let's some B of G. It doesn't matter for our purposes at the moment. Okay, some number of parameters. Let's call these parameters tau i's. So there is a metric G mu nu, which is a function of tau I. And every metric you can write down with this manifold, all that matters is this is a finite number of parameters. We will derive how many, we'll work it out. Okay? All that matters is the finite number of parameters, and the claim is that every metric on such a manifold is while and diffeomorphism invariant to one of these. So the space of metrics on these manifolds forms an equivalence class, forms shells of equivalence classes. The equivalence classes are by our gauge transformations, diffeomorphism and while. In general, you cannot. In general, there isn't a unique equivalence class. The parameter set are equivalence class. Okay? But finite number of parameters. Okay? So for every such equivalence class, we'll choose some standard metric. And then we will have to do eventually the integral over the tau i's. Okay? So we'll choose some g mu nu 0 of tau I for every equivalence class. And now the next thing we want to do, and then we will use gauge transformations to gauge fix to this g mu nu 0 of tau I, be left with an integral over tau i's. The first question we're going to address is how do we do this gauge fixing? Yeah, please go ahead.
This diagram that we have over there, are we imagining that out at infinity we connect it back to itself so it's compact?
No. This tube went on forever. It's the magic of conformal transformations that compactifies it.
Do we demand that this be an orientable surface?
Yes, at the moment I'm demanding that it's an orientable surface. At some point we will generalize our discussion to allow non-orientable manifolds. But we're doing the simplest case first. Right now it's orientable. Yes. What? Fine. You see, let's first do some crude counting. The crude counting tells us that the number of, if we've got a metric, it's got 3 functions. The number of gauge parameters is also 3 functions because there are 2 diffeomorphisms and 1 while transformation. So naively you would expect that any metric can be taken to any other by diffeomorphisms and while transformations. However, these naive arguments can be wrong not by measure 0 in the space of functions of 2 variables. Okay? And depending on your topology of your manifold, mathematicians understand how to answer this question very well. We will soon understand how to answer it very well. Okay? And depending on the topology of your manifold, you're sometimes wrong. Sometimes you can't go from every metric to every other by while and diffeomorphism, but there are equivalence classes of such metrics. These equivalence classes are labeled by finite number of parameters. These are tau i's. So what you can do, what gauge fixing will allow you to do, is to take you to a standard representative at any given tau I. But then you'll still have to integrate over tau i's.
Just sum over tau I, because
Tau is a continuous parameter. Okay, it's like the modulus of a torus. What, the space of taus you're asking? Yes, that's an interesting question. We'll come to that. Yeah. It's called moduli space. And moduli space will have to be in appropriate sense compact in order for everything to work. And that is the heart of the subtleties that Ashok has been uncovering with IR divergences of the last 2 3 years. Extremely. Okay. This is an interesting and subtle question. Okay. Fine. So, what are we going to do? We're going to replace, what we want to do is this. We want to replace our integral over all metrics, d g mu, with an integral only over d tau.
that's an ordinary integral, not a functional.
That's what we want to do. Okay? How do we do it? Well, we do it using the Faddeev-Popov trick. What? See, we've got the integral over metrics, and we want to use gauge freedom to help us do that integration. Okay? So we're going to use the Faddeev-Popov trick. So what we want to do is this. Consider the following thing. Start with g mu nu of tau, g mu nu 0 of tau, the distinguished metric at every given tau. Okay? And delta function. So we start with g mu 0 of tau times some gauge transformation. This gauge transformation means both while and diffeomorphism transformation, minus any metric and we integrate over both d tau and d omega and we put some other factor, okay, which will be a factor which depends on tau and which will basically depend on tau, and tau is our moduli.
Tau is the moduli. And if you have moduli, then confirm. Omega is a joining of diffeomorphisms.
Omega is all gauge transformations.
All rations.
Okay, diffeomorphisms and while transformations, and we've got right. So what we want to do is to do integrate. You know, we've got a space of metrics. It's foliated into equivalence classes. We integrate over the equivalence classes, over each element in one class, and we integrate over the classes. We generate the space over all metrics. So this delta function will somewhere click.
And you have this extra delta function that's because
For measure.
the delta for the measure, and because the delta function is not on tau. Like had it been delta of tau minus tau 0,
Exactly.
then there would have been no measure.
Then there would have been no measure. Exactly.
It's just that.
It's just that.
And presumably it's a functional integral over omega and an ordinary integral over tau.
It's a functional integral over omega and an ordinary integral over tau. Absolutely correct. Okay. So this is what we want to. This is the. This we want to find. Okay. The strategy is going to be to find a delta that makes this equal to 1 for every g mu. That delta, as you know, is called the Faddeev-Popov factor. For the Faddeev-Popov determinant. We want to find such a delta. Once we found such a delta, we will take this identity and insert it into our path integral. Okay? It will be an obvious fact that we will prove, but it's an obvious fact, that this delta, which is a function of tau, will not be a function of omega. Why is that? Because the gauge invariance of Faddeev-Popov determinant. Right. So let's see. I'm coming to it. Let me just outline the whole strategy first, and then do it. Okay. Good. So now what we will have is this object here. We have this delta function that we insert into our path integral. And we insert this whole identity into our path integral. Then we use this delta function to do the path integral over g. Okay? So now g is just replaced by our standard g, g standard metric gauge transform. But the whole integral here is gauge invariant. So the gauge transformation does nothing. So you can just replace this g by a standard integral. Okay? So then that has got rid of the integral over g. Okay? We just insert the standard g here. The d omega just gives you a volume factor. In really what we wanted was this divided by volume of omega. So that d omega will give you a volume factor which will cancel that volume of omega.
That is independent of everything.
That's independent of everything. It's just volume of some symmetric group. Okay? So all we'll be left with is the same thing, gauge fixed, but with this additional factor. Okay? And this additional factor is non-trivial and will contribute to everything we discuss and will give us a lot of fun. Okay? So the first thing that we want to do is to work out what this Faddeev-Popov determinant is. Okay? So let's see. Is this a job for today? Maybe not. Okay, so next class what we will do is we will analyze this Faddeev-Popov determinant. Okay? Understand what it is, and then after that just add it to the action here. Okay? And we've got a modified action with only x mu's and a Faddeev-Popov determinant, and then we will proceed. Okay? But maybe next class. What? How is the integral over g? So we've got this delta function. We put that in there. Use the delta function to do the integral over g. Do you understand this equation? So then once you've got this, you put that in here. Use that delta function to. We just replace, with this has a 1 here. We replace 1 by this. And the key point is that then the integral over omega will factor out. Okay. Yeah. Okay. Let's.
Is it that because d tau d omega is always diffeomorphic invariant?
The measure is diffeomorphism invariant.
This part of it.
What?
This is diffeomorphic invariant.
This part. D tau is has nothing to do with diffeomorphisms. This part is diffeomorphism.
That is the assumption
Which will make this invariant. Exactly. So the change of variables does it. Exactly right. This is the usual story.
Usual story, but that is assumed.
That is assumed that you are able to find a measure in the space of diffeomorphisms.
Like R measure.
Exactly.
Yes, because R measure is invariant. I mean, something like that.
Yeah. So what we're going to do is sometimes called the naive derivation, because we won't very carefully look at questions of what this measure means and so on. But the attitude we will take is this: we will follow reasonable steps and get a final formula. Then that formula is the one that will be completely well defined and will stand. And that formula will pass zillions of checks. In the end, if you give me rules for an S matrix that obey all the rules that is well defined and agrees with unitarity. Okay? It's an interesting S matrix. We will find it. And has gravity. Okay, so let's continue next.